Thank you very much. Thank you very much. Okay. Hello and welcome everyone. My name is Evangelos Goulas and I am a civil engineer. And today we're going to show you an automated feature in Diana in order to go through the conceptual and the final design stage of arch dams using Diana. And let's start with the overview. And first we're going to show the main concepts of a double curved arch dam. Then we're going to show how we develop the entire automated process, and in order to demonstrate it, we're going to show a case study. And we're going to conclude with the benefits and if you have further questions. But before that, we want to draw a poll about, in your practice, what is the common dam structure that you want to draw a layout for. Okay, thank you very much. And right now we can go and start with the background. First of all, what is an arch dam? Actually, it is a curved dam that we put in narrow valleys mostly, and we have two main types. The first one is the single curvature arch dam, which is curved only in plan, and this is what we can see from the picture. This is the plan view of a single curvature arch dam, and here you can see the upstream phase, which is connected to the water, and the downstream phase. By looking at the side view, we can see one of its sections and see that the single curvature arch dam is consisted mostly from straightforward lines, creating a trapezoidal shape. And at the same time, we have the double curvature arch dam, which is curved in plan but in elevation at the same time. And again, we have in the plan view the same picture, because both of the dams, they have the same picture for the plan view. But at the same time, the double curvature arch dam, it is curved in elevation, as we said. So the upstream line and the downstream line, they're curved. And right now, we can go and see some of the main characteristics of the double curved arch dam. And if the valley is narrow enough, then it is the thinnest concrete dam type we can use for this valley, for this location. And in addition, we don't need any reinforcement because the entire dam is under compression. And last, that the loads are transferred to the abutments by strengthening and compressing the entire structure. For example, if you're going to have a very simple arc where this is, for example, the hydrostatic pressure, then all of this load will be transferred to the two abutments from each side. And as you can imagine, a double curved arch dam can be described through many different formations, like circular or parabolic equations. For this process, we're going to use the modified parabolic function, and the main advantage for this is that by only defining 2 points, we can define the parabola. And these 2 points, we can see them, for example, in a plan view of the parabola. And this is the symmetry point, which is the point of the symmetry, and the focus point, which is the center point. And by knowing these 2 points, we can draw this parabola. And one more advantage is that the endpoints, as far as they go further from the reference plane, from the symmetry axis, they always towards the abutments. I have to point out at the same time here that the circular equations can be easily adopted to the process, so this is not a problem for the process. And right now, when you have a double curved arch dam, you have a massive structure which has a very complicated geometry. And for this reason, somehow, we have to divide it into some parts so we can control its geometry much more efficiently. And these are the 4 main parts we divided our geometry. First of all, we have the crown cantilever section. Then we have the main geometry or main parabolas, the abutment thickening or side parabolas, and the dam rock interface or foundation area. But let's take a closer look to each one of them. And we started with the crown cantilever section. And actually, it is the tallest cantilever in the dam, and it is usually located in the stream bed. And we call it the center of the dam. And why is that? Because if we're going to go and see the side view, then the upstream line, which is in connection to the water, and the downstream line, they're the 2 lines that they contain all of the symmetry points of our main parabolas for the upstream and the downstream phase. And right now, we can go and see the main geometry or main parabolas, as we said, which actually described the upstream and the downstream phase entirely. So, by looking at plan view of a random elevation I, we can see that in the crown cantilever, we see the symmetry point of the upstream and the downstream parabola, and at the same time they share the same center. And in this way, by knowing these 3 points, we can generate the 2 respective parabolas. And by doing this process for all of the different elevations, we can go and see the side view, where we see again the crown cantilever section, but at the same time, the very important thing is that we see the line of main centers. And by knowing these 3 lines, we can entirely know the upstream and the downstream face of the dam. And right now, regarding the abutment thickening or side parabolas, which is used in the downstream phase, and we use it when we want to add concrete locally in order to strengthen specific areas. And here, for example, it is the plan view of, again, a random elevation I, and you can see that the 2 dashed parabolas, they refer to each side. So this is the left-hand side parabola, and this is the right-hand side parabola. And by using this, you can see that this part, this dashed part, is added, and more concrete is added for this parabola. And the last but not less important main part, it is the dam rock interface geometry, or the foundation area, which connects all of the endpoints of the upstream and the downstream phase. And by having a foundation area, we know how deep is the dam inside the rock. For example, in the plan view, you can see the footprint of the dam. For example, here you can see that this is the riverbed, and the upstream foundation line contains, as we said, all of the upstream endpoints of the main phase, and respectively for the downstream foundation line. And right now, as we described the main stages, the main concepts, of the double curved arch dam, we can go and draw another poll for how many layouts are you doing for the preliminary design stage, and then we're going to draw another poll for how many layouts are you going to use for the final design stage. And right now we can go further without any other polls. Okay, so it's time to start with the design stages, and based on the USBR method, which is actually the United States Bureau of Reclamation method, we're gonna divide our design stages into 2. First, we're gonna have the preliminary design stage, where the best fitting dam is determined in terms of casting and excavation volume. And then, by having this initial layout, we can go and start with the final design stage, where the initial dam will reshape till the desirable stress levels are reached. But let's take a closer look to the workflows of this process. So starting, first of all, we have to actually pick a reference site. And then, based on this reference site, we can pick as many locations as we need in order to generate a layout for them. But in order to make it a bit more clearer, we can go and see the picture, which is actually the top view of a surface. And here you see that all of these dams were generated based on our process. And you see how powerful it is, because no matter where you're going to put it, a dam is going to be generated. And then, by having the best fitting dam from these locations, we can go and evaluate the results. The evaluation will be done based on which is the most economical location in terms of casting and excavation volume. And after this stage, this is going to be the best alternative which is going to be used for the next stage. But before going there, it's really nice to see how easily you can control the entire geometry of these initial layouts. And this is done by only controlling 6 basic variables. So in your dialogues, for example, you can put the Y start, which is the location of that you're gonna focus on. In addition, you have the Z base, which is the elevation of the dam. Then you have the height, which is the height of the crown cantilever section. As we said, it is the center of our dam. And then you have these 2 variables, which is the L excavation and L excavation minimum, which control how deep is the dam is inside the rock. And then we're going to have the theta axis, where the theta axis is very important because, as you can see, it can rotate the entire dam around the crown cantilever section. So in this way, for each location, we can define which is the best fitting dam. And right now, having found the best preliminary alternative, we can go and starting with the final design stage. And first, we're going to put interface elements between the dam cantilevers and the dam and the rock interface. And then we're going to run our stress analysis, from which we're going to actually evaluate our stresses based on two stress constraints. The first stress constraint, it is that the tensile stress should be less than 1 megapascal. And the second, it is that the compressive stress should be less than the concrete strength we used for the dam. And if these stress constraints are not satisfied, then we can go and redefine the crown cantilever section, the line of main centers, and we can add side parabolas. These steps can be done all together or each one of them. And then again, we're going to go generate the new interface elements because we have a new shape. And again, we're going to run an analysis. And this fine-tuning optimization will take as many iterations as we need until we're going to satisfy the stress constraints. And right now, let's take a closer look how we can redefine these three parts that I mentioned. First of all, here we can see how we can thicken the entire crown cantilever section. And this dashed red line, it shows that how we can actually thicken the crown cantilever section. And by making it even thicker, then the entire dam is becoming more resistant against the hydrostatic pressure, for example. And right now, for the line of main centers, let's take an example of a plan view, again from a random elevation I. And here what you can see is that as we're going to start changing the location of the center, what is happening is that if this distance between the symmetry point and the center is becoming larger, then the respective parabola will become wider and vice versa. And by doing this process for all of the different elevations, then we can go to the side view and actually see that redefined line of main centers. So by having this line of main centers, the redefined line, then we can actually reshape the entire dam by making it steeper and wider in the critical areas. And right now, for the side parabolas, we can see again the same picture as we saw from before, and right now we can explain it. So for each side, we have to find a side center and a tangent point. And based on these 2 points, these red dashed parts will be added for this location. And for example, if we're going to focus in the right-hand side and see the side view, we can go and see 2 new lines that are added in our process, where it is actually the line of tangent points and the line of side centers. By knowing these lines, we can add concrete around the foundation area along the dam height by actually keeping the smoothness of the downstream face, which is very important, because if in this stage we're going to introduce any dimples, then we're going to create some stress concentration areas that we don't want to have there. And this actually was the end of the process. But right now, let's go to see a case study. And as we said, first we have to find a reference site. And this site should be obtained based on 3D topographic maps. There are 2 ways that we can obtain this topology. And the first one is that if you already have the information, because you surveyed the field, or from Google Maps. And some simple criteria for the site location of the dam, they should be characterized based on the length, the width, and the depth of the valley. For example, in our process, we used actually the second option, where actually we went and found a reference site through Google Maps. And for this reason, we used SketchUp. As you can see here, we see the picture of Derner Dam, which is located in Turkey. And then we converted it through SketchUp into a 3D surface that we exported into a CAD file, and we took out the cloud of points. And this cloud of points is going to be used from our process. So, going back to our case study, we found the reference site in Vikos Gorge, which is located in Greece. And here, for example, you can see this cloud of points that we discussed before in the process from Google Maps. And by using the tools from Diana, we imported this cloud of points into a Bezier surface. and this surface is very accurate in order to simulate this topology. And this is the top view, where you can clearly see, first of all, the riverbed and the side rocks. So it is time to pick the locations in order to start creating our layouts. And we're going to focus on three different locations. And because the river flow is supposed to be from the bottom to the top of the surface, first we have location A, where an asymmetrical dam to the right-hand side is generated. Then we have location B, where a more or less symmetrical dam is generated. And then we have location C, where an asymmetrical dam to the left-hand side is generated. So, and right now, let's see a very important tool from our process. And this is what we said from before, because the axis angle should be defined in order to find the best fitting dam in terms of concrete and excavation volume. And this is done based on two geometric constraints from the USBR method. Because, if you already know, it is the 30 degrees rule, where if we're going to see the plan view of the dam, and here we see the abutment, and the angle between the tangent and the average rock contour should be larger than 30 degrees. And this should be applied for both of the sides. And these two β angles should equal to each other. And that's why here we have this small table where we signify what are the colors in our graph. And the red refers to none of these criteria are satisfied. The orange means that only one of them is satisfied, and the green, we're going to focus on actually, that both of the criteria are satisfied. So let's go back to the graph right now, and let's see what is happening. First of all, the horizontal axis, it refers to the axis angle, or how much rotated is the dam around the crown cantilever section. While at the same time, the vertical axis, it is the volume of the concrete or the dam or the excavation volume. And pay attention, because right now we're talking about some millions of concrete, some millions of cubic meters. And by starting from the lower bound, which is minus 25 degrees, if we're going to go to a smaller number, then we cannot generate a dam, because what is happening is that the dam is so rotated that the endpoints are not inside the rock anymore. While if we're going to start increasing the axis angle, then we can see that these lines are created, which refer every time to a different dam and excavation volume. And for the first area, we see that we have the red color, which means that none of these geometric constraints are satisfied. And then, increasing and increasing, we can see that we enter the orange area where only one of them are satisfied. And at last, we have the green area that we're going to focus on. And of course, because if we're going to rotate again even more, we're going to end up again with a very rotated dam that we don't want to have. So, by focusing on the green areas, we can see that here we have the blue arrow that it says that for this axis angle, which is minus 10 degrees, we have the most economical or the best fitting dam for this location. So this is the best fitting layout only for this location. And perhaps you can imagine, you can see that this is more or less a straightforward line, a parallel line to the horizontal axis, but as we said, because we're talking about millions of cubic meters, even the slight difference is very important, and we can actually save some concrete volume. And right now, we can go to location B and do exactly the same process as before. So we're starting from the lower bound, and we're increasing the axis angle, and we're passing from the red zone to the orange zone, and at last we find the green zone again. And here we're going to pick the 24 degrees for the axis angle, so we can generate the most economical dam. What you can observe here, compared to the previous graph, is that this range from minus 24, minus 14 to 40 degrees, it is much larger. And this is because the topology around this location, it is much smoother, which actually ends up to a larger range for the axis angle. or else, or in other words, we have more actually alternatives for this location. And right now we can go to location C and see again this powerful feature, because we're gonna start again from -6, and right now we can end up to 20. But you can see here how smaller is the range of this axis angle, because what is happening in this area is that the topology right now is much steeper. And this reflects, of course, the valid values as well. And that's why here the selection of the best fitting dam is much faster. And as we have the best fitting dam for each layout, we can compare them to each other so we can find which is the best alternative of our initial stage. And as we can see very easily is that location B gives us the most economical concrete and excavation volume at the same time. And you can see that right now we're talking about a dam which is around 1.2 millions of cubic meters for concrete volume only, while for the excavation volume is around 0.25 millions of cubic meters. And this location B from now on will be used as the best alternative for the final design stage. And right now we can start with the final design stage, where an iterative process took place, as we saw from the workflow, where more than 60 different iterations were performed. And what we did there is that we modified the final variables progressively. And what I mean with that is that every time for each one of these iterations, we added a small amount of concrete so we can decrease the tensile stresses in the critical stress areas, while the main goal is to add the least essential concrete volume in these critical areas I mentioned until the stress constraints are satisfied. And the stress constraints are the same as we saw from before, where the tensile stress should be less than 1 megapascal and the compressive stress should be less than the concrete strength of the dam. But before going to the iteration, it's very nice to see some more powerful and automated tools of this process. Because as you may already know, a concrete arch dam is not built as a whole body, but we have to split it in alternate blocks, the dam cantilevers, as you can see in the picture. So this process is done automatically every time you're going to generate a different layout. And as you can see here, this is the dam through the process, and these are the different dam cantilevers. For example, if we're going to zoom in one of them, you can see that this is the top view, and for example, the adjacent surfaces are helical. Continuing, here are the interface elements and how we put them in each of these layouts or iterations. We have two different categories. The first one is concrete, and actually are the common surfaces between the dam cantilevers, and we're going to connect them to each other so we can simulate possible slidings. And then we have the second category, which is called the concrete rock. And of course, as you can imagine, we connect or disconnect interfaces between the dam and the rock. And here we have two different subcategories. The first one is called side interfaces, where actually we disconnect the rock from the upstream phase and the downstream phase of the dam, so both of the solids around these areas can act independently, while we're going to connect the dam to the rock only through the foundation area. So in this way, all of the loading will be transferred through the foundation area to the rock. And before going to the iterations, it's nice to see some of the common properties, because as you can imagine, in order to have comparable results, we have to have common properties. And for example, here you can see the linear material properties of our models. And yeah, for example, we use concrete with 30 megapascal of strength, while at the same time, the interfaces, these are made up, we took out them through some empirical methods. And at the same time, you see that here it's the constitutive model of the nonlinear interfaces, because we're using no tension interfaces. And right now, the load combination we have used self-weight and hydrostatic pressure. The analysis type, it is structural nonlinear static. The mesh type, it is hex-quad linear elements. The rock mesh size will be relatively coarse because we don't focus on the rock, so we chose 100 meters. And the dam mesh size, it is 10 meters. And we want it to be relatively fine because we're going to focus on the dam. And right now, we can see what are going to be the critical stress areas we're going to focus on every time in every iteration. And we have the red circle in the downstream phase, which is located in the central area of the dam. And here we're expecting high tensile stresses in the downstream phase. And the same thing, but for the green circles, that they're located in the upstream phase. And as you see from the picture again, here you see that they're around the foundation area for both of the sides. And right now, at last, we can go and see the iterations. I'm not going to show all of them, but only 4 characteristic ones. And iteration 0, it is the initial shape of the dam from the initial stage. Then iteration 1 and 2 are 2 intermediate iterations where the stress constraints are not satisfied. While iteration 3, it is the final dam layout where all of the stress constraints and the geometric constraints are satisfied at the same time. Here in the table, you can see all of the different values of the concrete and the excavation volume, but let's visualize them. And this is shown in the graph. So the blue columns are the concrete volume, and the orange color is the excavation volume that we found for each one of these iterations. And as it is logical, because every time we're adding more concrete, we see that every time both of the volumes are increasing until in the end we have the final iteration 3, where the concrete volume, for example, is 50% more than the initial volume in iteration 0. And right now we can go and see what is happening with the stress constraints. As we said, the allowable tensile stress, it is 1 megapascal. And right now, based on the stress critical areas we showed before, we're gonna find the maximum upstream tensile stresses and the maximum downstream tensile stresses. And here you see the different numbers which are in red because they don't satisfy the constraint, while they're satisfied only for the last one. While at the same time, for the compressive stresses, you can see that we don't have a problem. As we said, we used a concrete strength of 30 megapascal, and this is satisfied from the first iteration. And again, we're going to visualize the results, where the red line is the tensile stress constraint, while right now the orange columns refer to the upstream phase, while the yellow columns refer to the downstream phase. And as you can see, the downstream phase is much more critical for our process. And right now we can go and visualize at last how these different layouts look like. And this is the top view of these 4 different characteristic iterations. And here we see the initial shape. And as we're adding and adding more concrete, we see that this is thickened accordingly. For example, if we're gonna focus on the light gray area, which is actually the crest of the dam, we see that as we're adding concrete, this is thickened. And at the same time, we see in the downstream phase that the side parabolas are added, because here you see that we cannot even see the downstream phase, while when we go to iteration 1, we see that the downstream phase is more apparent. And as we go into iteration 2 and 3, then in the end we see that in iteration 3, these parabolas around the foundation of the dam, they're much steeper. And the same goes for the bottom view, because here we see the dam layouts for all of the characteristic iterations, and this is the foundation area. And no matter how much concrete are we going to add, we can always take a very smooth foundation area. And this is very important because in this way we do not add any geometric anomalies in our process. which may occur to high tensile stresses areas. And right now we can see the average displacement field DEXYZ for each one of these iterations. And we're going to focus on the highest displacements, where actually are located exactly where we were expecting them. And this is around the crown cantilever section. And we're starting with 12 centimeters, and we drove to around 9, then to around 8, and in the end, for our final design layout, we have around 6.69 centimeters. Because the dam, by adding more concrete, it became more resistant, of course. And right now we see how we actually found the maximum tensile stresses for each one of these dams in the critical areas. And these are the views for the in-plane principal stresses in the upstream phase. And here we see that these are the circled areas we saw from before. And here we found every time what is the maximum tensile in-plane stress. And we're starting with around 1.9 megapascal. We drove to 1.5, and we reach until the end we are below the 1 megapascal, which is the stress constraints, as we said. The same goes for the in-plane principal stresses for the downstream phase. And as you can see here, these are the critical areas for the downstream phase. And as we said, it is much more critical, and that's why we're starting with a value of 3.5 megapascal. And we're dropping until it is below 1 megapascal, exactly as we needed for the stress constraints to be satisfied. And the last visualization of the results, it's about the interface relative displacement DUNZ. And here actually you can see the openings of the interfaces, where in iteration 0, they're located around the dam base and the side rocks. But as we're adding concrete, we can see that this area is getting smaller, while all of the openings are happening closer to the toe of the dam. And by adding even more concrete, we see that this area has diminished. And in the end, for iteration 3, we can see that these openings are happening only around the crown cantilever section. And this was more or less the case study that we just explained. But before going to the benefits, I would like to show you a summary of the automated process, because we can actually describe it just in one slide. And as we said, we're going to start with a dam site, and we're going to generate the topology. And based on this topology, we're going to pick our initial locations, where we're going to find the best fitting location for each one of them based on the graph we showed from before. And by finding the initial layout, we're going to use it in the iterative process of the final design stage to generate the model every time with the interfaces and run the analysis. And then actually we can generate our final design and optimal shape. And right now about the benefits of the automated process. And we're going to start to say that the design process gets automated because both of the stress constraints and the geometric constraints are satisfied. In addition, the modeling effort is drastically reduced because the only data we need is the topographic data, and at the same time to define the basic and the final variables for each one of these layouts. And then we can have unlimited layouts regardless of the locations. Because if we're going to have a proper topology, no matter where we're going to pick the location, a dam layout will be designed. And then we have an intuitive set of variables, because by having only a limited number of variables, we can actually control the entire geometric shape of the dam, and every time to reform it based on our will. And we have an optimized analysis time, because even with a fine mesh, some thousands of elements, the model generation can be done in less than 1 hour, performing all of the stress, performing every type of stress analysis. So you can imagine that in less time, we can run more models. And this entire process was based on assessing, or not, sorry, based on creating a new dam. But it can be easily adopted in order to assess an existing dam. The only thing that we need is the topographic data of this location and at the same time the geometric data of the existing dam. And then we can use it in our process in order to generate it. And then the last benefit, it's about the automated report generation. And what I mean with that is that by using Diana, you can easily generate all of these results and geometric data into a Word file that it can be done for you automatically through Diana. Actually, this was the entire presentation, and thank you very much for your attention.